Welcome to Transcribe Me 2020 Exam Audio Test B. Before you start the exam, be sure to read the set of instructions at the very top of the exam screen to prevent any mistakes. Each question contains detailed information as to how to properly complete the question and section as a whole. Read each question carefully before you continue.
If you have various objects in space, what does space look like? How does the universe evolve? I mean, cosmology has turned into a science since the time of Einstein. I mean, before that, people had ideas about the universe, and you'll often see people refer back to the same notions that occurred earlier. But really, it's now a scientific theory. So it's true there were tremendous breakthroughs in the last century. But if you know what the universe is made of, that's going to tell you how, to some extent, how it evolves. And if you know how it evolves, that gives you constraints on what it's made of. So it's not like there's one field of physics and you can do it in complete isolation from another one. I mean, part of what makes the field rich and enjoyable for me is that you can ask questions not just about elementary particles, but also about cosmology. And when you begin to think about ideas about the whole global nature of space-time, you can't help but think about cosmology as well.
You're writing a book called Warp Passages, Unraveling the Mysteries of the Universe's Hidden Dimensions. I love three words there. One, unraveling the mysteries, and secondly, hidden dimensions. What are you trying to find out? What is it you want to tell us that we're going to be amazed by if it proves right?
We're really trying to understand, it sounds very vague, but what is the fundamental nature of matter and forces? What are the fundamental forces and why are they related in the way they are? So we're trying to understand more about gravity, for example. Why is gravity so much weaker than all the other elementary forces we know about? That is to say, the three other elementary forces we know about, electromagnetism, and weak and strong nuclear forces. Gravity is far weaker. I mean, if you think about it, you can pick up a paperclip with a tiny magnet competing against the entire Earth. And the fact that you can jump up and down. I mean, gravity is not a strong force. Although it dominates things, it's only because there's big, massive objects.
It's not a strong force where we are and might be a strong force somewhere else?
Yeah, so there's a question of how it manifests itself. And if there's a big, energetic object, it seems strong. But if you took two elementary particles and compared the force of electromagnetism and the force of gravity, I mean, gravity is negligible. You don't even have to consider it. You throw it away. But why is that? Why is gravity so much weaker? And for particle physicists, it's even more mysterious than just why is it so much weaker. If you naively just sat down and calculated how you expect the forces to be related, you would think that those forces should be about the same strength. So there's a big question that particle physicists have is why is gravity so much weaker than the other forces? And so that's one question we have, but we have other questions too. What is the fundamental nature of gravity? Ultimately, we do want to know what's a quantum theory of gravity that combines it with quantum mechanics. We want to understand what the universe is made of. What is the dark matter? What is the dark energy that's not carried by matter? So there are some pretty big questions that are driving us.
Okay. This multiple dimensions idea, I think even Einstein said there were 4 dimensions. And then string theorists came along and said there are 10 dimensions.
Yeah, string theorists seem to think that there are at least 10 dimensions.
And how many do you think there are?
I like to leave it an open question. I like to say, what have we measured? What do we know? And could there be other dimensions out there? And there certainly could be other dimensions out there. It might be 10 or 11 space-time dimensions, as string theorists tell us now. So why is it that physicists today are really thinking about extra dimensions? Well, one of the reasons is that we think it might actually have something to do with our universe. I mean, that's, I think, for me, the most important reason. But another reason is, in fact, string theory. And it's introduced the idea that maybe dimensions really are there because that's the only way the theory makes sense. But string theory has also introduced something else. In the 1990s, the physicist Joel Polchinski realized that there were these other objects in the context of string theory called brains. That word is sort of related to membrane. And the idea is that there could be, even if you have higher dimensions, even if you have a 5th spatial dimension or a 4th spatial dimension out there, there could be objects in the universe called brains that don't spread throughout the entire universe. And maybe stuff is stuck on those lower dimensional surfaces. And that's one idea that we got very excited about.